Okay, so let's talk about a couple more complicated problems here. Some things that often happen in elimination method and in solving systems in general is things don't look exactly like we want them to look. They got fractions. They don't have opposite signs already. The terms aren't solved for variables on one side and constant on the other. So we're going to look at those three cases, not in that order, but see how to approach these problems. So let's look at the first one. 2y equals -6 minus 5x, and 2x equals -5y plus 6. It's obviously a system of linear equations, and we're asked to solve it, to find the point of intersection of these two lines. But what's the appropriate choice? I mean, should we do substitution? Well, I wouldn't. It's kind of hard to solve those for a variable because we'd have fractions floating around everywhere, and that's not super fun. So probably not that. But in order to use elimination method, you should have seen this in the last few videos. We need to get all of our variable terms on one side. We need to get them in order, so lined up vertically, x's over x's, y's over y's, equals over equals, numbers over numbers. That's where elimination method works the best. So both of these don't look so great. So let's look at the top linear equation. I don't like that the -5x is over here on the right-hand side. Let's move that, because right now there's no way to set our variables up vertically. Y's are not on top of y's, they're on top of x's. And x's are not on top of x's, they're on top of constants, and constants are on top of y's. That looks really crummy. So elimination method works in standard form, where all our variables are on one side and constants are on the other. So what would it take? Well, if I want to leave my constants, I'm going to add 5x to both sides. So sometimes when we're approaching a problem and setting this up for the appropriate method, either substitution or elimination, we're moving around some terms to make this more manageable. Substitution, I'd put it off to the side because I don't want to solve that for a variable. Elimination method is going to work here, but we need some setup. That's not too bad. If we just add 5x, then that translates to a 5x plus 2y, keep our signs correct, equals -6. Generally, and it doesn't have to be this way, but generally we like x's first and y's second. That way when we move our terms around, they're already lined up for us. Now here, our second equation. I don't like that the y is over on the right-hand side. I like the constant, that's fine. But let's go ahead, let's add 5y to both sides. Let's keep our x's first, that's fine. Let's add our 5y second, that's okay. And now our constant is just 6. So this is set up a lot better. I have variables on one side, they're in standard form. I get x's first, y's second, they're lined up vertically. I have constant on the right-hand side. Now, oh man, what's the appropriate choice? Because we've been talking a lot about the appropriate choice for terms. We need to make some opposite terms in order to simplify this problem. Now, don't jump to the conclusion that there's no solution because it looks weird. It does look weird. There's 5 and 2, 2 and 5. Well, it's going to be no solution because it looks strange. Well, don't judge a book by its cover. Don't judge the problem like that. We need to make an appropriate choice to make opposite terms, sure. Now, what is the appropriate choice? There's not a great one, but here's what you need to notice. Both of these pairs of terms have exactly the same sign. We had to add on both of them. They're all positive. So no matter what we do, we're going to have to multiply one of these equations by a positive and one of these equations by a negative. It doesn't matter which one. So basically it comes down to your preference. Do you want to make the y's opposite terms or do you want to make the x's opposite terms? I'm going to pick the y's. Why? I have no good reason. Just the one that popped in my head right now. So I'm going to make the y's opposite terms. Now, do you notice the reason why I said there's not an obvious choice? Because if I look at the LCM here for my x's, 5 and 2, that's 10. Look at the y's, 5 and 2, that's also 10. So either way, I'm going to have to make this 10. So that's the number we're trying to get, but we also need them to be opposites in that we need opposite signs. So sure, I'm going to be multiplying both of these equations. I know that I can't multiply 2 and get 5. I can't multiply 5 and get 2, not by whole numbers, and we're trying to stick with whole numbers here, integers. So I'm going to have to multiply, in order to get my LCM on my y's, I'm going to have to multiply to get 10 here by 5 and here by 2. Now, if you just notice that I'm missing something, you are on the right track. That means you're learning about this. I need opposite signs as well. So these systems don't work well with elimination method if they don't have opposite signs. We're not going to eliminate a variable. Remember, elimination, you have to add opposite terms to eliminate them. That's what's going on. Now, whichever one you choose doesn't matter as far as which one you make positive or negative. You can make this -5 and this +2, or this +5 and this -2. It doesn't matter. Don't make both of these numbers negative, because then you'll change both pairs of signs and end up with the same problem. Now, I will tell you, I'm going to pick this to be -5, and the only reason I'm doing that is because I have a negative constant. And I know that a negative times a negative is a positive, which will lead me to one less negative. Huge deal? Not at all. It's just something to be aware of to make your life a little bit easier. So did you catch that? Whether I do -5 or -2, this would create +10, this would create -10. That's great. This would create -10, this would create +10. That's fine. The only problem would be here, where you get -10 and -10, not opposite. Or remain +10, +10. Again, not opposite. So let's go ahead, let's make this -5 and +2. If we kind of distribute to both sides, we're really multiplying both sides by -5, we'll have -25x, okay. We'll have -10y, that looks great, that's exactly what we wanted to happen. And we'll have +30 by nature of a negative times a negative is a positive. I didn't forget to multiply the constant. I'm multiplying this by a negative, that looks good. Now the second equation, 2 times 2x, well that's 4x. I've got 2 times 5y, oh that's plus 10y. And then 2 times 6 is 12. Now, that looks pretty darn good. And that might have been unexpected. Sometimes we want to jump to conclusions like, wow, that's the same, it's going to work out to 0. It doesn't at all. When we create a certain pair of terms to be opposite terms, the other ones don't play along in the same fashion. They get multiplied by numbers that, well, that's not 2 to make that 10, that's not 5 to make that 10. So they don't match up how you might think they would. So don't give up on the problem. Go through the process I'm telling you. Get your variables on one side. Great. Get them lined up vertically. Not a problem. Be careful of the signs. You need opposite terms. There was no obvious choice here. I picked y's because that's the first thing that popped in my head, but I am noticing that they're both positives. I need to multiply one of these equations by a negative. I'm letting that go to every single term, every one of them. Same thing here, every single term, but I need opposite signs to create opposite signs. Now, once I've got that, let's add. This gives us -21x. 10y's are gone. -10y plus 10y, that's 0. We've eliminated the entire term. And then we have 42. If we divide by -21, we get x equals negative, man, if I can write, x equals -2, and we've created the first half of the point of intersection for our system of linear equations. Now, what equation do we use to find the missing one? These, all the way back there. Pick the originals. Always pick the original equations when you're solving for the rest of your point. It doesn't super matter which ones you do, but those will have the smallest numbers, and they're typically the easiest ones to use. Do you have to? No. What you do have to do is make sure that your terms are opposite terms if you're adding the system. What you also have to do is, once you finish this point of intersection, to check your work, you have to use those, and we'll be doing that in just a minute. So I'm going to look back. I've got my x solved for. I want to solve for y. Because this is nearly solved for y, I'm going to use this top equation. You don't have to, but it's a good choice. So I know that x is -2. Now, lots of signs going on here. I'm going to be careful. That's -6 plus 10. 2y would equal +4. Y would equal +2. Now let's check it out. Let's make sure that that works. So I need x to be -2 and y to be 2. And I need those coordinates to work in both of these linear equations. I need that point to be on both lines, because if that point is on both lines, it is the intersection that solves the system. So -2 for x. Let's see, that would be Negative 6 plus 10, because let me show that. Let's see if that works. I plug in 2 for y, I get 4. I plug in negative 2 for x, I get 6 plus 10. That's 4. Okay, I know that that points on that line. Now here, negative 2 for x, that's negative 4. 2 for y, let's see, that's negative 10 plus 6, that's also negative 4. Now I'm assured that that is the correct point of intersection for that system. So checking points in the original equations, the original system, that's a big deal. Moving on a little bit, what happens if you have something that you really, really want to be opposite terms? They're just not. Don't work too hard on a problem like this one. This looks pretty well set up for, actually, it could be either one. You can make substitution method pretty easily by subtracting 3y or subtracting 6y. Do you have to do substitution? No. It's also fairly well set up for elimination method. Your variable, verify that with me. Your variables are on one side. They're lined up. You have x's over x's, you have y's over y's, you have constants over constants. The only problem is, what? Well, you don't have opposite terms. You really want there to be. Right here, it looks pretty close. So when that happens, when you have terms that are identical, refrain from adding the system. If you added it right now, you'd get 2x, you would get 9y, and you'd get 1. That's a problem because elimination method requires you to actually eliminate a variable, just like substitution method did. When you substituted, an entire variable disappeared from your equation. It was replaced with an expression that has the same variables which you were given in your original equation. So when you replace that with substitution, you basically eliminate a variable. That has to happen. So when you have the case where you have literally identical terms on both equations, just multiply one of them by negative 1. It does not matter which one. I do the top one because it'll get rid of that negative. That is the only reason. So when I multiply the top equation by negative 1, notice I have to do nothing with the bottom one. If I multiply the top by negative 1, we'll have negative x, we'll have minus 3y, we'll have positive 1. Bottom equation didn't need to change. I only needed to change one term to make these opposite. After that, this is exactly what we're looking for, lined up with opposite terms. We add, negative x plus x is 0, that's great. Negative 3y plus 6y is 3y equals 3. We know that y is 1. If y is 1, we can use one of the original equations, even one of these, but it's best to use these. They're typically easier. I'll use the bottom one. So x plus 6y equals 2. Let's plug in that y equals 1. I really want you to end with an ordered pair, showing me that you understand what's going on. We're finding the point of intersection for these two lines. That's exactly what's going on. If you were to graph this, you would get that point as where these lines cross. Now let's make sure that we're right. So plug in negative 4 for x, plug in 1 for y. Plug it into the original equations. Negative 4 plus 3 is negative 1. We got that. Negative 4 plus 6 is 2. So I know that that's the correct answer. That's important that you understand the idea about when we're multiplying by a negative and when we're not. We're always trying to get opposite terms. I hope it's making sense so far. Now, at this point, I'm going to erase the board. I'm going to put on a problem that we've actually already done. We did this problem with substitution method. If you want to go back and check out the video, it was the one with fractions that took a long time. It was like, are you freaking serious that we have to do this? Yes, but substitution method was absolutely the wrong choice. I did it on purpose so that when you saw that video, like, man, when I have fractions, substitution method kind of sucks. And you're right, it sucks a lot because you can't get rid of the fractions. With elimination method, we can, we should, and it's way, way much more better, all right? It's like awesome. It's a lot nicer. So we're going to take a moment, I'm going to erase this and we'll do that one. I'll show you how much faster elimination method is when we're dealing with fractions. That's not to say elimination method is always better. It's just that sometimes it is a better choice in some examples and sometimes substitution is a better choice.
Okay, so you're given that, and you go, well, let's identify it. I always think about what we're doing first anyway. It's a system. There's two variables in each equation. There's two equations. That's a system of linear equations. And it looks nasty. And we have done that before. We've done that in substitution method. And it took a long time, and it was not easy. Let's look at why it's not easy for substitution. And graphing. I mean, would you really want to graph that? That's crazy. Don't graph that. That's silly. Don't do that. Substitution is almost as crazy because you'd have to solve that for a variable, or you'd have to solve this for a variable, and it's not fun because you can't really clear fractions very effectively in the substitution method. You have to solve for a variable itself. Well, that means that you're going to ultimately be dividing at some point, and you're going to be creating fractions. Even if you clear them, you're going to be recreating them, and then you'll have to deal with them in a substitution manner. Not so fun. Elimination method saves us from that. So I'm going to say this. If you see a lot of fractions and you do not have something solved for a variable already, do not do substitution method. So when I'm looking at this, I'm going system, yeah. I'm seeing fractions, man, right there. If I'm not solved for a variable already, I'm immediately thinking elimination method. And I taught you a great way on how to clear fractions way back when we talk about solving linear equations. The way that we clear fractions is by using the LCD of your fractions. So in other words, no fraction, hey, that's a denominator of 2, no fraction. Use your LCD and multiply everything by 2. Now, when I say everything, I mean everything in that equation. Both sides, every term, much like what we're doing when we use the LCM to find opposite terms. Same idea, just bound in one equation so as to clear the fractions. Here, no fractions, you're going to get 6x. Here, fractions, yes, but notice how the 2 and the denominator of 2 are going to simplify. You're going to get 1y. On the right-hand side, you can't miss the numbers, okay? 2 times 2 is 4. Now, the same thing happens here. Denominator of 2, no denominator besides 1. Denominator of 2, our LCD there is also 2. We're going to multiply every single term. I'm also going to move my negatives to the top of fractions. It's good practice so you don't lose them. Multiply every single term. That's both sides distributed and on the right-hand side, so everything by 2. Here, fraction gone. Denominator simplify. You get negative x. No denominator, no simplification. You multiply, you get 10y. Right-hand side, 2's are gone, we get 19. Now, you might be thinking, it doesn't look great, but that looks a whole lot better than this because you have a way to go about solving it the rest of the way. Here, you kind of question, what in the world should I do? Should I solve for y, solve for x, solve for x, solve for y? None of it's a good choice. Here, we can at least say, well, my variables are lined up. They're all on one side. It looks reasonably set up for elimination method if I'm trying to solve this system. And I have at least a way to make my variables opposite terms by multiplying one equation by just one number. Now, which one would you pick? Would you want to make the y's opposite terms or the x's opposite terms? The answer is whichever one takes smaller numbers to multiply by. In either case, you'd be fine. You could multiply this by 10 and create my y's the same. I can multiply this by 6 and create my x's the same. I'm going to choose the 6 because I always like multiplying by smaller numbers when I can. So I'll multiply that whole equation by 6. That means every single term exactly like we did with fractions. We're just given a little different look. Now one thing I want to make sure that you understand this. What if this was not, what if that wasn't a negative? Is that still a 6? No, it's not still a 6 because if you multiply by 6 now, you get 6x and 6x, you would not eliminate. We'd have to make this a negative 6 in order to make opposite terms. That's got to sink in. You need the opposite part of this. So when necessary, like we did in the first example over here a while back, you need to multiply by negatives so as to get your opposite signs. Okay, so let's multiply through. I know that my 6x minus y equals 4. That's not going to change. But I know that I'm multiplying every single term by 6. That's both sides by 6. That's negative 6x, man, it looks awesome, plus 60y, okay, that kind of sucks, equals, oh wow, what is that, 114 or something?
That doesn't look fun, but it's a whole lot more fun than doing fractions. Let's see what happens when we add these together. I know they're going to eliminate because I set it up that way. We set it up so that we would have opposite terms. If we add our terms together, 6x plus negative 6x, 0. It's gone. It's eliminated. I love it. We have 59y, and I certainly hope that's 118. Large numbers, but just trust the system. Trust what I'm teaching you. If you just divide, y equals 2. We have half our point already. That's nice. Now, let's plug this into, I'm going to break my rule, okay? I'm not going to plug this into my original equation because that's got a lot of fractions. I'm going to plug it in right here, but I will be checking this in my original equation to make sure that we're right. So plug it into here. So y equals 2. Okay, that's 6x minus 2 equals 4. If I add the 2, and divide by 6, we get 1. So, okay, that's 2. Plug in the 2 for my y. Add, divide, we get 1. Now, we used a different equation than my original. We're going to for sure double check in the original equation to make sure that we're right. So we want 3 times 1 minus 1/2 times 2. So 3 times 1, that's 3. 1/2 of 2 is 1. 3 minus 1 is 2. I know that this point is on that line, that linear equation. Check in the next one. So 1/2 times x, that's 1/2. 1/2 times 1 is 1/2 plus 10. That's 10.5. Oh wait, is that negative? That's what I did. So negative 1 plus, that's 9.5. 19/2. So I know that that point's also in this equation. Sorry about the missing negative there. It was in purple, I didn't even see it. So 19/2, I know that that point is the point of intersection for that original system of linear equations. I really hope that this made sense on when you use elimination method. You see, substitution method is not bad, and I'm not saying that at all. What I'm saying is it's used best when you have a system of linear equations where one equation is already solved for a variable, or where it's very easy to solve for a variable, like you have to add one thing and you're done. When you don't have that, when you have fractions, when you have variables scattered everywhere, elimination method is typically your best option because you can multiply out your fractions. Because you can multiply both equations by a number and make opposite terms. When you do that, you add the entire system, it automatically eliminates a variable. You're left with one variable. You divide one time, you get 1/2 of your point of intersection. Plug that into one of your equations, you solve for the other half. It's very elegant, it's very nice. The last thing I need to talk about. What happens, now I'm going to change the problem, so let's just pretend this happens. What happens when you do this and you add your system and you get one of these two things? What happens when you add your system and everything eliminates? Absolutely everything. What happens if you add your system and everything eliminates is that you had the same exact equations. So if you have the same exact equations, you had the same line. Those two lines, if we're looking for the point of intersection, those are the same lines. That means you had identical lines. That would give you infinite solutions by having identical lines. So if everything eliminates and you get 0 equals 0, that's a true statement. That's a true statement all the time. That's infinite solutions. Let's say that you eliminate all your variables and you're left with a number. I'm just going to come up with 3. Let's say you're left with that, like 0 equals 3. That's a nonsense statement. That's never true. So if you eliminate all your variables and you still have a constant, so 0 equals a number, that's a no solution case. So I've been prefacing this over the last 2 videos that What happens if everything eliminates? What happens if you get rid of all your variables? If your variables, both pairs of your variables do match up, then you'll get either no solution if you have a nonsense statement. 0 never equals 3, ever, no matter what you do. 0 doesn't equal that number. That's a no solution. If you get 0 equals 0, that meant that you have identical lines. They're exactly the same because everything matched up perfectly. That's infinite solutions. So, infinite solutions by having identical lines. No solution by having parallel lines. These lines will never intersect. They're not the same, but they'll never cross. That's how to interpret those two things. I really, I need you to get this stuff in order to move on, because we're going to talk about applications in the next video. So practice substitution, practice your elimination method, really put in the work, go through these examples again, make sure that you can do them, especially the hard ones. Don't shy away from them, challenge them. And I'll get you back on doing some word problems in the next video. Have a great day.